Imagine you're standing in your backyard at night, looking up at the stars. Those pinpricks of light you see? Some of them traveled billions of years to reach your eyes. But here's something that'll make your brain short-circuit. Those galaxies are now 46 billion light-years away from us, even though the universe is only 13.8 billion years old. Wait, what? How did they get so far away if nothing, absolutely nothing, can travel faster than light? This isn't some fringe theory or science fiction. This is observational fact, confirmed by thousands of astronomers using the most precise instruments humanity has ever built. And it gets weirder. In the first fraction of a second after the Big Bang, the universe didn't just expand faster than light. It expanded at speeds that make light look like it's standing still. We're talking about the universe growing from smaller than an atom to larger than a galaxy in less time than it takes light to cross the width of a proton. Your physics teacher told you nothing can break the speed of light. Einstein's special relativity is built on this absolute speed limit. It's been tested millions of times. Every particle accelerator, every GPS satellite, every observation of the cosmos confirms it. So how did the universe itself violate what seems like nature's most fundamental law? Did the universe cheat? Did it find some cosmic loophole? Or is everything we think we know about the speed limit of reality completely wrong? Here's what's about to blow your mind. The answer involves space itself doing something that sounds impossible, time behaving in ways that defy imagination, and a revelation about what speed actually means that will fundamentally change how you see reality. By the end of this journey, you're going to understand one of the most profound mysteries in all of physics, and you'll never look at the night sky the same way again. Before we dive deep into this cosmic rabbit hole, do me a favor. Smash that like button right now. Hit subscribe and turn on notifications, because what we're about to explore is going to challenge everything you think you know about space, time, and the nature of reality itself. And drop a comment telling me where in the world you're watching from and what time it is for you right now. I'm genuinely curious how far across the globe this mind-bending journey is reaching. Let's start with what seems like a simple question. What does it actually mean to say nothing can go faster than light? When Einstein published his theory of special relativity in 1905, he didn't just randomly pick a speed limit. He discovered something fundamental about the fabric of reality itself. Light doesn't just happen to be the fastest thing. The speed of light, exactly 299,792,458 meters per second, is actually the speed of causality itself. It's the speed at which cause and effect propagate through the universe. Think of it like this. Imagine you're playing a video game, and there's a maximum frame rate the game can process. No matter how fast things seem to move on screen, everything is fundamentally limited by how quickly the computer can update the game state. The speed of light is reality's frame rate. It's not just about how fast light moves. It's about how fast anything can influence anything else. When you flip a light switch, the electromagnetic signal telling the light bulb to turn on travels at the speed of light. When gravity from the sun pulls on Earth, that gravitational influence propagates at the speed of light. Even the force holding atoms together, the strong nuclear force, can only act as fast as light allows. This speed limit isn't arbitrary. It emerges from something deeper, the relationship between space and time. Before Einstein, people thought space and time were separate things. You could measure how far apart two objects were in space, and you could measure how much time passed between two events, and these were completely independent measurements. Einstein realized they're not separate at all. They're woven together into a single thing called spacetime. And once you understand spacetime, the speed of light stops being a speed limit on motion and becomes something far stranger. It's the rate at which you trade space for time. Here's where it gets weird. When you move through space, you're actually rotating through spacetime. Imagine spacetime as a graph where one axis is space and the other is time. Everything in the universe is always moving through this graph at the same total speed. Yes, you read that right. Everything moves through spacetime at the same speed. But here's the trick. You can move more through the space part or more through the time part, but the total always stays the same. When you're sitting still in space, you're moving through time at maximum speed. That's why time passes normally for you. When you start moving through space, you have to move a bit slower through time to keep the total constant. That's time dilation, and it's been measured thousands of times. The speed of light is what happens when you use up all your space-time motion moving through space. At that point, you have zero motion left for moving through time. This is why photons, particles of light, don't experience time at all. From a photon's perspective, if it could have a perspective, it's emitted and absorbed in the same instant, even if billions of years pass for us watching from the outside. The photon reaches its destination the same moment it leaves its source, because when you're moving at light speed, there is no time. Now here's the critical part that most people miss. This speed limit, this cosmic speed limit of light, only applies to objects moving through space. It's a restriction on how fast things can move from one location to another location through the space between them. Einstein's special relativity specifically talks about how objects move through a fixed spatial background. The rules say that no object with mass can accelerate to light speed, and no information can be transmitted from point A to point B faster than light can make that journey. But notice the sneaky assumption built into that statement. It assumes space itself stays fixed. It assumes the stage on which motion happens doesn't change. And that assumption, right there, is where the universe found its loophole. Einstein's special relativity describes motion through space, but it doesn't restrict what space itself can do. That requires a different theory, general relativity, which Einstein published in 1915. And general relativity revealed something absolutely mind-blowing. Space isn't a fixed stage. Space is dynamic. Space can stretch, compress, bend, and yes, expand. And when space expands, it can carry objects apart faster than light without those objects actually moving through space at all. Think of it like this. Imagine two ants on a rubber band. If one ant crawls toward the other ant along the rubber band, there's a maximum speed the ant can crawl. That's like the speed of light. But now imagine someone grabs both ends of the rubber band and stretches it. The ants get farther apart, but neither ant is violating its crawling speed limit because they're not crawling. The rubber band itself is stretching. The ants are standing still on their local piece of rubber band, and the distance between them increases because more rubber band is being created in the middle. This is exactly what's happening in the universe. Galaxies aren't flying through space away from us, like shrapnel from an explosion. The space between galaxies is expanding, and the galaxies are just going along for the ride. Each galaxy is essentially sitting still in its local region of space. But the distance between galaxies increases because new space is continuously being created everywhere. And here's the kicker. There's no speed limit on how fast space itself can expand. The prohibition on faster-than-light travel only applies to motion through space, not to the expansion of space itself. This distinction might seem like a technicality, like we're playing word games, but it's not. It's fundamental, and it's been confirmed by decades of observations. In the 1920s, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, made a discovery that changed everything. He observed distant galaxies and measured their light. He found that the light from these galaxies was shifted toward the red end of the spectrum, a phenomenon called redshift. The farther away a galaxy was, the more its light was redshifted. Hubble realized this meant the universe was expanding. Distant galaxies were moving away from us, and the farther away they were, the faster they were receding. But here's what Hubble didn't fully understand at the time, and what took decades for physicists to work out. These galaxies aren't moving through space. The redshift isn't caused by galaxies flying away from us like rockets. It's caused by the expansion of space itself, stretching the wavelength of light as it travels. Imagine drawing a wave on a rubber band and then stretching the rubber band. The wave gets longer, its wavelength increases. That's exactly what happens to light traveling through expanding space. The space through which the light travels expands while the light is in transit, stretching the light waves, shifting them toward the red. This means that distant galaxies can recede from us faster than light without violating any speed limit because they're not actually moving. We're not moving either. The space between us is expanding, and we're both just sitting in our respective neighborhoods of space, watching each other get farther away. Astronomers have measured galaxies receding from us at multiple times the speed of light. Not because they're moving that fast, but because the space between us and them is expanding that fast. And this happens routinely, everywhere in the universe, right now. But wait, if this is happening now, just from the normal expansion of space, what happened at the very beginning when the universe was young? How fast was space expanding then? And this is where we come to the shocking answer that spawned this entire journey. In the first moments after the Big Bang, space expanded so fast, so incomprehensibly fast, that the universe grew from smaller than a subatomic particle to larger than a galaxy in a fraction of a second. Not in the poetic, exaggerated way people sometimes describe fast things, literally, precisely, based on mathematical models and observational evidence. The universe went through a period called cosmic inflation, where space expanded faster than anything in physics should allow, except it didn't violate any laws, because the laws only restrict motion through space, not the expansion of space itself. And here's what's going to melt your brain. We have evidence this happened. Multiple lines of evidence. The cosmic microwave background radiation, the afterglow of the Big Bang that fills the entire universe, has patterns in it that can only be explained by inflation. The large-scale structure of the universe, the way galaxies are distributed across space, matches the predictions of inflation. Even the fact that the universe is so uniform in all directions, something that seems impossible if different regions couldn't have influenced each other, makes perfect sense if inflation happened. Because during inflation, the entire observable universe came from a tiny region that had time to smooth itself out before inflation blew it up to cosmic scales. We're about to go deeper to understand exactly what inflation was, why it happened, and what it means for the nature of reality. But take a second right now to let this sink in. The universe found a loophole in the cosmic speed limit, not by breaking the rules, but by operating in a way the rules don't restrict. Space itself can expand as fast as it wants, and in the first fraction of a second of cosmic history, it expanded so fast it makes light look like it's frozen in time. To understand cosmic inflation, we need to talk about energy, and specifically about a very strange kind of energy that most people have never heard of, but which dominates the universe. But before we get there, let's build some intuition about what energy actually is and how it relates to the expansion of space. You probably think of energy as the stuff that makes things happen. It takes energy to move a car, to heat your home, to power your phone. And you've heard of the conservation of energy. Energy can't be created or destroyed, only changed from one form to another. Earn gasoline, you get heat and motion. Charge a battery, you store chemical energy. Drop a ball, gravitational potential energy converts to kinetic energy. The total amount always stays the same. But here's something weird that most people don't realize. The expansion of the universe seems to violate conservation of energy. As the universe expands, the total volume of space increases. If space contains energy, like the energy in electromagnetic fields or the energy in matter, then as the volume grows, the total energy should decrease because it's spread over more space, right? That's true for most kinds of energy. Radiation, like light, it's diluted as the universe expands. The cosmic microwave background radiation used to be hot, high-energy gamma rays right after the Big Bang. Now, it's weak, low-energy microwaves because the universe is expanded and spread that energy over a much larger volume. But there's a weird kind of energy that doesn't dilute. It's called vacuum energy or dark energy, and it's energy that's inherent to space itself. Every cubic meter of space contains a certain amount of this energy, and when space expands and creates more cubic meters, it creates more energy. Yes, you heard that right. As the universe expands, the total amount of dark energy increases because there's more space, and each piece of space carries energy with it. This seems to violate conservation of energy, and in a sense it does. But general relativity allows it because energy conservation in an expanding universe is more subtle than in a fixed space. Now, this dark energy does something incredibly strange. It pushes space apart. Most energy gravitates. It pulls things together. Matter attracts matter through gravity. Radiation, even though it doesn't have mass in the traditional sense, still gravitates. Everything with energy causes space to curve and pulls things together. But vacuum energy does the opposite. It has a property called negative pressure, and this negative pressure acts like anti-gravity. Instead of pulling space together, it pushes space apart. Think of it like this. Imagine a balloon filled with normal air. The air pressure inside pushes outward, making the balloon expand. But the elastic tension in the balloon walls pulls inward, resisting the expansion. Eventually, these forces balance, and the balloon stops growing. Now imagine a balloon where the air inside has the weird property that the more you stretch the balloon, the stronger the air pressure becomes. The expansion itself creates more pressure, which causes more expansion, which creates even more pressure in a runaway process. That's basically what vacuum energy does to space. The more space expands, the more vacuum energy there is, which pushes space to expand even faster, creating even more vacuum energy. In the universe today, dark energy exists, but it's very weak. It causes the expansion of the universe to accelerate slowly, a discovery made in 1998 by two teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, who won the Nobel Prize in 2011 for this discovery. They observed distant supernovae, exploding stars that serve as cosmic distance markers, and found that the universe's expansion is speeding up. This acceleration is caused by dark energy, but it's a gentle acceleration. The universe expands about 7% faster every billion years. But in the very early universe, according to the theory of cosmic inflation, developed primarily by Alan Guth in 1980 and refined by Andre Linde, Paul Steinhardt, and others in the years following, there was a much stronger form of vacuum energy. This inflationary vacuum energy was thousands of orders of magnitude more powerful than the dark energy we see today. And when this energy dominated the universe, it caused space to expand exponentially fast. Not just accelerating, but doubling in size every tiny fraction of a second. Here's what exponential expansion means. Imagine you have a piece of paper. Fold it in half. That's 2 layers. Fold it again. 4 layers. Fold it again. 8 layers. Each fold doubles the thickness. After just 10 folds, you have over 1,000 layers. After 20 folds, over 1,000,000. After 40 folds, your piece of paper would be thicker than the distance from Earth to the Moon. That's exponential growth. Now imagine this happening to the universe, but instead of doubling every fold, it doubles every 10 to the negative 34 seconds. That's a decimal point followed by 33 zeros and then a 1 in seconds. An unimaginably short time. During inflation, the universe doubled in size approximately every 10 to the negative 34 seconds. This happened for a duration somewhere between 10 to the negative 36 and 10 to the negative 32 seconds. Let's take a middle estimate and say inflation lasted 10 to the negative 34 seconds and the universe doubled about 100 times during this period. 100 doublings means the universe grew by a factor of 2 to the power of 100. That's a number with 30 digits. The universe expanded by a factor of 10,000 trillion and less than a trillionth of a trillionth of a trillionth of a trillionth of a second. To put that in perspective, the observable universe today is about 93 billion light years across. Before inflation, the region that would become the observable universe was smaller than a proton. Inflation took something smaller than the smallest subatomic particle and blew it up to the size of a soccer ball, or possibly even larger, all in less time than it takes light to cross the width of an atomic nucleus. The expansion was so fast that if you could somehow stand in that primordial universe and watch, you wouldn't see anything moving. You'd see the space between everything stretching so rapidly that light couldn't keep up. Neighboring points in space that were close enough to touch would be ripped apart faster than light could cross the gap between them. Now, you might be thinking, okay, but why did this happen? What caused inflation? And this is where things get really interesting, because the answer involves quantum mechanics, the physics of the very small, intruding into cosmology, the physics of the very large. In the quantum world, fields permeate all of space. You've heard of the electromagnetic field, the field that carries electromagnetic waves and photons. But there are other fields too. There's an electron field, a quark field, a Higgs field that was discovered in 2012 at the Large Hadron Collider. Fields are the fundamental entities in modern physics. Particles are just excitations, ripples in these fields. The inflationary theory proposes that there's an inflaton field, a hypothetical field that filled the early universe. Like all quantum fields, the inflaton field has potential energy. Imagine a ball on a hill. A ball has potential energy because of its position. If you give it a nudge, it rolls down the hill, converting potential energy to kinetic energy. The inflaton field worked the same way, except the hill is a description of the field's energy at different field values, not a physical hill in space. In the very early universe, right after the Big Bang, the inflaton field found itself high up on its potential energy hill. It wasn't at the bottom, the stable equilibrium position. It was displaced, stuck in a high energy state. And this high energy state acted like vacuum energy. It had the weird property of negative pressure that pushes space apart. So the universe started expanding exponentially fast, driven by the energy in the inflaton field. As the universe expanded, the inflaton field slowly rolled down its potential energy hill, like a ball rolling down a gentle slope. But here's the crucial part. During the time it was rolling, the field's energy stayed approximately constant, and this constant energy density in every cubic meter of space drove the exponential expansion. Eventually, the inflaton field reached the bottom of its potential energy hill. It oscillated around the minima, like a ball settling in a valley, and all that energy in the field converted into ordinary particles, radiation, and heat. This is called reheating, and it's the point where inflation ended and the hot, dense, expanding universe of the traditional Big Bang picture began. So the Big Bang, in the inflation picture, isn't really the beginning. It's more like a phase transition, the moment when the inflationary period ended and the energy driving inflation got converted into all the matter and energy we see in the universe today. The true beginning, if there was one, is whatever caused the inflaton field to get displaced to high energy in the first place. And that's still a mystery. Now here's what's beautiful and mind-blowing about this theory. It solves multiple problems with the traditional Big Bang model that had puzzled cosmologists for decades. First, there's the horizon problem. The cosmic microwave background, the radiation left over from the early universe, has almost exactly the same temperature in all directions. It varies by only 1 part in 100,000. This means that the entire observable universe was at thermal equilibrium early on, with every region at the same temperature. But in the traditional Big Bang model, without inflation, regions on opposite sides of the sky were never close enough to interact. They were outside each other's light horizon. They couldn't have exchanged heat to reach the same temperature. It's like finding 2 people on opposite sides of the Earth, wearing exactly the same outfit, having the same hairstyle, speaking the same obscure dialect, and then discovering they never met, never communicated, and have no shared history. How did they end up identical? Inflation solves this. Before inflation, the entire observable universe was tiny, much smaller than the distance light could travel. All the regions that are now spread across the sky were once in close contact, able to thermalize and reach the same temperature. Then inflation happened, and these regions were blown apart so fast they ended up outside each other's light horizon. They've been causally disconnected ever since, but they remember the common temperature they shared before inflation separated them. Second, there's the flatness problem. When we measure the geometry of the universe, we find it's flat. Not flat like a pancake, but flat in the sense that parallel lines stay parallel. The angles of a triangle add up to 180 degrees, and the overall curvature of space is 0. But for the universe to be flat today, it had to be extraordinarily flat in the early universe. Any tiny deviation from flatness grows over time. If the universe was even slightly curved early on, it should be obviously curved now. The fact that it's flat to within measurement precision means that in the first second after the Big Bang, the universe's curvature was fine-tuned to do better than 1 part in 10 to the 60. That's like balancing a pencil on its tip and having it stay balanced for 1 billion years. Why would the universe start out so perfectly flat? Inflation solves this too. Exponential expansion takes any curved space and flattens it. Imagine the surface of a balloon. It's curved. But if you inflate the balloon to an enormous size, any small patch of its surface looks flat. If you inflate the balloon enough, even a region the size of a continent would appear flat to someone standing on it. Inflation inflated the universe so much that even if it started out curved, the observable universe is now just a tiny patch of a vastly larger whole, and that patch appears flat. The universe might still be curved on scales, far larger than we can observe, but our observable region got stretched so much that any curvature is invisible. Third, and this is subtle but important, there's the structure problem. The universe has structure. Galaxies, clusters of galaxies, vast cosmic webs of matter separated by enormous voids. This structure grew from tiny density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter, grew denser, and eventually collapsed into galaxies and stars. But where did those initial tiny fluctuations come from? Why was the universe not perfectly smooth? Inflation provides an answer, and it's one of the most profound connections between quantum mechanics and cosmology ever discovered. Quantum mechanics tells us that fields fluctuate. Even in empty space, quantum fields jitter around due to the Heisenberg uncertainty principle. These fluctuations are tiny, but during inflation, they got blown up to cosmic scales. A quantum fluctuation in the inflatoned field, initially smaller than a proton, got stretched by inflation until it was light years across. These quantum fluctuations became the seeds of all cosmic structure. Every galaxy, every star, every planet ultimately traces its origin back to a microscopic quantum jitter that got amplified to cosmic size by the exponential expansion of inflation. And here's what makes this more than just a beautiful theory. We can test it. Those quantum fluctuations stretched by inflation left an imprint on the cosmic microwave background. They created slight variations in temperature across the sky. And when we map these variations, we see a pattern that matches the predictions of inflation. The Cosmic Background Explorer satellite in the 1990s, the Wilkinson Microwave Anisotropy Probe in the 2000s, and the Planck satellite in the 2010s all mapped these fluctuations in exquisite detail, and the patterns match inflation's predictions to remarkable precision. The fluctuations have the right amplitude, the right scale dependence, and the right statistical properties. We're not done yet, not by a long shot. There are deeper questions we need to answer. What exactly is the inflaton field? Why did it start displaced from equilibrium? Did inflation have a beginning? Or did it happen eternally in some larger multiverse? But before we dive into those mind-bending questions, I want you to pause and realize what we've just uncovered. The universe expanded faster than light, not by breaking the cosmic speed limit, but by exploiting a loophole written into the structure of reality itself. And this wasn't just speculation. We have evidence. We can see the fingerprints of inflation written across the sky in the cosmic microwave background. The quantum jitters of inflation became the galaxies we see today. You, me, the Earth, the Sun, the Milky Way, all of it exists because a quantum field jittered and inflation stretched that jitter to cosmic size. That's not a metaphor. That's our origin story, written in the language of physics and confirmed by observation. So we've established that space can expand faster than light, and that inflation caused a period of exponential expansion in the early universe. But let's go deeper. What does this mean for causality? What does it mean for how different parts of the universe can influence each other? This is where things get philosophically weird, and where the distinction between moving through space and the expansion of space becomes crucial to understanding what's happening. In Einstein's theory of relativity, there's a concept called the light cone. Imagine you're at a particular point in space at a particular moment in time. That's an event in spacetime. Now, from that event, you can send out a signal. If you send it at the speed of light, the fastest possible signal, it will spread out in all directions, forming an expanding sphere. If you plot this in a space-time diagram with time going upward and space spreading outward, the paths of these light signals form a cone shape. Everything inside this cone, both in the future and the past, is causally connected to you. You can influence things in your future light cone, and you are influenced by things in your past light cone. Everything outside the light cone is causally disconnected from you. You can't reach it. It can't reach you, not yet at least. This light cone structure is fundamental to how cause and effect work in the universe. If something happens outside your light cone, it can't affect you until enough time has passed for light from that event to reach you. And this makes perfect sense in a universe where space is fixed or expanding slowly. Your light cone grows outward at the speed of light, gradually encompassing more and more of the universe. But during inflation, something bizarre happened. Space expanded so fast that regions which started inside each other's light cones, close enough to influence each other, got pulled outside each other's light cones. They got separated faster than light could travel between them. It's not that signals between these regions traveled faster than light. It's that the space between them expanded so rapidly that even light traveling at its maximum speed couldn't keep up. A photon traveling from one region toward another would find that by the time it traveled any distance, the expansion of space had increased the distance to its destination more than the distance it had covered. Think of it like this. Imagine you're running on a treadmill, trying to reach the front of the treadmill. But the treadmill is accelerating, and it's accelerating faster than you can speed up your running. Even though you're running at your maximum speed, you're actually getting farther from the front of the treadmill because the belt is moving backward beneath you faster than you're moving forward. That's what happened to light during inflation. Light was traveling as fast as it could, but space was expanding faster, so regions that started close together ended up farther apart, beyond each other's reach. Now, here's where your brain should start tingling. This means that the observable universe, the region of space from which light has had time to reach us since the Big Bang, is much smaller than the actual universe. We can see about 93 billion light years in any direction. That's our observable universe, our cosmic horizon. But the total universe is much, much larger. How much larger? We don't know. It could be 1,000 times larger, 1,000,000 times larger, or even infinite. Inflation took a tiny region and blew it up so large that we can only see a small fraction of it. And here's what's wild. There are regions of space that we will never, ever be able to see or influence, not because they're too far away in principle, but because the expansion of space is currently accelerating due to dark energy. Right now, galaxies beyond a certain distance are receding from us faster than light because of the expansion of space. Light leading those galaxies now will never reach us because the space between us and them is expanding faster than the light can cross it. We are surrounded by an event horizon, a boundary beyond which we cannot see or interact. And as time goes on, this horizon is getting closer. Galaxies that we can see today will eventually cross our event horizon and disappear from view, not because they're destroyed, but because the light they emit will never be able to reach us across the exponentially expanding gulf between us. This has profound implications. It means the universe is much larger than we can ever observe. It means there are potentially infinite other regions, other galaxies, even other observers, that we will never know exist because we are causally disconnected from them. And if inflation was as powerful as we think, it means the universe is so large that, given enough space and the random fluctuations that create structure, there are almost certainly other regions where the same random arrangements of matter occurred. Regions where there's another planet like Earth, another person like you, reading something like this. Not metaphorically, but statistically, given infinite space and finite possible configurations. This is called the infinite universe hypothesis, and it's a direct consequence of inflation combined with the probabilistic nature of quantum mechanics. If space is infinite and quantum fluctuations create structure randomly, then every possible arrangement of matter will occur somewhere, infinitely many times. There are other versions of you out there, in regions so distant that light will never cross the gap. And this isn't science fiction. This is where the mathematics of inflation and quantum mechanics leads, if you follow it honestly. Now, some physicists find this troubling. It makes the universe seem less predictable, less knowable. If everything that can happen does happen somewhere, then what's the meaning of any particular observation or event? Other physicists find it exhilarating. It means the universe is vaster and richer than we ever imagined. Both reactions are valid. What matters is that this is where the evidence and the mathematics point. But let's bring this back to our central question. How did the universe expand faster than light? We've talked about space expanding and objects moving through space being different things. But there's a deeper question here. Is space a thing? Or is space just a relationship between objects? This is one of the oldest questions in physics, debated by Newton and Leibniz in the 1600s, and it's still not fully settled. Newton thought space was absolute, a fixed container in which objects move. Leibniz thought space was relational, just a description of where objects are relative to each other. Einstein's general relativity leans toward Newton's view in some ways, treating spacetime as a dynamic entity that can curve and stretch. But quantum theories of gravity, still being developed, might lean toward Leibniz's view, treating space as an emergent phenomena arising from deeper relationships. If space is a thing, then it can expand, and there's no speed limit on its expansion. If space is relational, then talking about space expanding is really talking about the relationships between objects changing in a particular way. Either way, the observational consequences are the same. Distant galaxies recede, light gets redshifted, and inflation stretched quantum fluctuations to cosmic scales. But the philosophical interpretation differs. Here's another layer to this. General relativity doesn't just allow space to expand, it requires it. Given the matter and energy in the universe, Einstein's equations of general relativity have solutions. And the solutions for a universe filled with matter and energy uniformly distributed are expanding universes. The equations don't allow for a static universe, at least not stably. Einstein actually tried to force the equations to allow a static universe by adding a cosmological constant, a fudge factor that exactly balanced gravity to keep the universe from collapsing or expanding. He later called this his greatest blunder when Hubble discovered the universe was expanding. But ironically, we now know the cosmological constant, or something like it, dark energy, does exist. It's just not large enough to make the universe static. It makes the expansion accelerate instead. So the expansion of the universe isn't some weird anomaly. It's a natural consequence of having matter and energy in a spacetime governed by Einstein's equations. And inflation is a particular phase in the universe's history when the dominant energy was vacuum energy with negative pressure, causing exponentially fast expansion. The faster-than-light expansion isn't breaking any laws. It's exactly what the laws predict should happen given the right initial conditions. Now let's talk about what happened at the boundary between inflation and the traditional Big Bang. Inflation ended when the inflattened field rolled to the bottom of its potential energy hill. At that moment, all the energy that was driving inflation, a truly staggering amount of energy, had to go somewhere. It couldn't just disappear. Energy is conserved, or at least approximately conserved in general relativity. So the inflattened field decayed. It broke apart into ordinary particles, photons, quarks, electrons, neutrinos, all the fundamental particles of the standard model of particle physics. This process, called reheating, flooded the universe with particles and radiation. The temperature skyrocketed. We're talking temperatures around 10 to the 27 degrees Kelvin, a billion degrees. At these temperatures, particles collided with energies far higher than anything we can produce in particle accelerators. Quarks and antiquarks created and annihilated each other. The Higgs field settled into its stable state, giving mass to particles. The fundamental forces, which may have been unified at even higher energies, began to separate into the distinct forces we know today: electromagnetism, the weak nuclear force, the strong nuclear force. And from this hot, dense soup of particles and radiation, the universe we know began to take shape. The universe continued to expand, but no longer exponentially. The expansion slowed down, governed by the matter and radiation now filling space. The temperature dropped. After about 3 minutes, the universe cooled enough for protons and neutrons to stick together, forming the first atomic nuclei, mostly hydrogen and helium. After about 380,000 years, the universe cooled enough for electrons to bind to these nuclei, forming neutral atoms. At that moment, light could finally travel freely through space without constantly scattering off charged particles. That's the light we see today as the cosmic microwave background. But here's something subtle and beautiful. Although inflation ended and the exponential expansion stopped, the initial boost from inflation never went away. All that expansion inflation created is still with us. The universe is vastly larger because of inflation. The tiny quantum fluctuations that inflation stretched cosmic size are still imprinted in the distribution of galaxies. In a very real sense, inflation set the initial conditions for everything that came after. The universe we inhabit is an inflated universe, and the properties we observe, from its flatness to its structure to its sheer size, are consequences of that brief but incredibly powerful exponential expansion. Let's do a thought experiment. Imagine you could rewind time and watch inflation happen. You wouldn't actually see much because the universe during inflation was nearly empty. The only energy present was the inflattened field energy, which is smooth and doesn't emit light. But if you could somehow mark 2 points in space and watch, you'd see them rush apart at an incomprehensible rate. After 10 to the negative 34 seconds, they'd be twice as far apart. After another 10 to the negative 34 seconds, twice as far again. By the time inflation ended, after perhaps 100 doublings, they'd be separated by a distance that light would take trillions of years to cross, and yet only a tiny fraction of a second would have passed. And then, at the moment inflation ended, the universe would suddenly blaze with light and particles as the inflattened field energy converted to matter and radiation. It would be the ultimate explosion, not in the sense of things moving outward through space, but in the sense of energy suddenly transforming from one form to another, flooding space with particles. That moment, the end of inflation, is what we traditionally call the Big Bang, even though it's not actually the beginning. This distinction is important. The Big Bang is not the moment when the universe came into existence. It's the moment when inflation ended and the hot, dense phase of the universe's history began. What happened before inflation, or what caused inflation to start, is still an open question. Some models suggest inflation emerged from quantum fluctuations in a pre-existing space. Other models suggest inflation is eternal, continuously happening in some regions of a vast multiverse, with our observable universe being just one bubble where inflation happened to end. Still, other models try to avoid the need for a beginning altogether, proposing cyclic universes or emergent spacetime from even more fundamental structures. We're not at the end of this rabbit hole yet. There are still layers to uncover. But take a moment to absorb what we've covered. Space is not a fixed stage. It's a dynamic entity that can expand, and when it expands, it can carry objects apart faster than light without violating any speed limits, because the objects aren't moving through space. Inflation was a period when this expansion happened exponentially fast, driven by a quantum field with strange properties. And this exponential expansion solved major cosmological puzzles and set the initial conditions for the entire observable universe. The universe is larger, older, and stranger than our everyday experience suggests. And the reason we can make sense of it at all is because physics, mathematics, and observation all point in the same direction. Let's shift gears and talk about something that might be bothering you. We've been throwing around terms like space-time, quantum fields, and exponential expansion as if they're well-established facts. But how do we know any of this is true? How can physicists claim to know what happened in the first tiny fraction of a second after the Big Bang, a time and place utterly beyond human experience? This is a fair question, and it's worth addressing because the evidence for inflation and the Big Bang is actually much stronger than most people realize. First, let's talk about the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, the oldest light in the universe. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, and at that moment, light decoupled from matter. Before this, the universe was so hot and dense that light couldn't travel far without scattering off electrons. But once atoms formed, light could stream freely through space. That light has been traveling ever since, and we can see it today coming from all directions in the sky. The CMB was predicted in 1948 by Ralph Alpher and Robert Herman, who were working out the consequences of the Big Bang theory. They calculated that if the universe started hot and dense and expanded, there should be leftover radiation from that early time, and it should have cooled to about 5 degrees above absolute zero by now. In 1964, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, accidentally discovered this radiation while trying to eliminate noise from a radio antenna. They detected a faint microwave signal coming from everywhere in the sky with a temperature of about 3 degrees Kelvin. This discovery earned them the Nobel Prize in 1978 and provided the first strong evidence that the Big Bang really happened. But the CMB is more than just a faint glow. It contains information. When we map the CMB in detail, we see tiny variations in temperature across the sky, about 1 part in 100,000. These variations are not random. They have a specific pattern, a statistical signature that tells us about the conditions in the early universe. And this is where inflation makes testable predictions. Inflation predicts that the fluctuations in the CMB should be nearly scale invariant, meaning the fluctuations should have roughly the same amplitude on all size scales, with a slight tilt. It predicts that the fluctuations should be Gaussian, following a bell curve distribution with no strong outliers. It predicts specific correlations in the pattern of hot and cold spots. And when we measure the CMB, we find exactly these properties. The Planck satellite, which mapped the CMB from 2009 to 2013, measured the fluctuations with extraordinary precision, and the data matches inflation's predictions to within a fraction of a percent. Moreover, inflation makes a prediction about the geometry of the universe. It predicts the universe should be spatially flat, meaning the sum of angles in a cosmic triangle should be exactly 180 degrees. We can test this by measuring the sizes of the hot and cold spots in the CMB. If the universe were curved, these spots would appear larger or smaller than expected. The measurements show the universe is flat to within measurement precision, exactly as inflation predicts. But that's not all. Inflation predicts that in addition to the density fluctuations we see in the CMB, there should also be gravitational wave fluctuations, ripples in spacetime itself, created by the same quantum processes during inflation. These gravitational waves would leave a distinct imprint on the CMB, a pattern called B-mode polarization. This hasn't been definitively detected yet, but several experiments are currently searching for it. If and when we detect the signal, it will be the smoking gun for inflation, direct evidence that the rapid expansion really happened. Beyond the CMB, there's the large-scale structure of the universe. Galaxies are not distributed randomly. They form filaments and clusters, separated by vast voids, creating a cosmic web. This structure grew from the tiny density fluctuations seeded by inflation. Computer simulations that start with inflation's predicted fluctuations and evolve them forward using the laws of gravity and gas dynamics produce structures that match the distribution of galaxies we observe. The Sloan Digital Sky Survey and other galaxy surveys have mapped millions of galaxies, and the patterns match what inflation predicts. Then there's the abundance of light elements. In the first few minutes after the Big Bang, during a period called Big Bang nucleosynthesis, protons and neutrons fused to form helium, lithium, and traces of other light elements. The amounts of these elements depend on the conditions in the early universe, specifically the density of ordinary matter and the expansion rate. When we measure the abundances of these elements in the universe today, in old stars and pristine gas clouds that haven't been contaminated by stellar processes, we find exactly the amount predicted by Big Bang nucleosynthesis. Helium makes up about 25% of ordinary matter by mass, exactly as predicted. This is a completely independent confirmation of the Big Bang model. And here's something remarkable. All these pieces of evidence, the CMB, the large-scale structure, the element abundances, they all fit together into a consistent picture. The same cosmological parameters that explain the CMB also explain galaxy clustering. The same early universe conditions that produced helium also produced the photons we see in the CMB. The evidence is overdetermined. We have more constraints than free parameters. If the model were wrong, it would fail somewhere. But it doesn't. Everything fits. Now, you might say, okay, that's all very impressive. But it still seems like we're extrapolating from current observations back to an unimaginably early time. How can we be confident? The answer is that we're not just extrapolating. We're testing the model in multiple ways, and every test it passes increases our confidence. In science, we never prove theories absolutely. We test them, see if they make successful predictions, and look for ways they might fail. The Big Bang model, and inflation as an extension of it, has been tested extensively and passed every test so far. But there are still unknowns. We don't know what the inflattened field actually is. Is it a completely new field, unrelated to any known particles? Or is it related to fields we already know about, like the Higgs field? We don't know what caused inflation to start. Did it begin from a quantum fluctuation? Was there something before inflation? We don't know how long inflation lasted. Different models give different answers, and we don't yet have enough data to distinguish between them definitively. And there's a deeper conceptual issue, the initial conditions problem. Inflation explains why the universe is flat, uniform, and filled with structure. But to start inflation, you need the inflattened field to be displaced from equilibrium. Why was it displaced? What set up those initial conditions? Some physicists argue that inflation just pushes the problem back without solving it. Others argue that if inflation is eternal, as some models suggest, then the initial conditions don't matter because inflation erases any prior information. This brings us to one of the most speculative and mind-bending ideas in modern cosmology: eternal inflation and the multiverse. Some versions of inflation theory, particularly those developed by Andrei Linde and Alexander Vilenkin, suggest that inflation doesn't just happen once. It happens continuously in different regions of space. In most regions, inflation continues forever, but occasionally, quantum fluctuations cause it to end locally, creating a bubble universe like ours. Inside each bubble, inflation has ended and a hot Big Bang phase begins, but outside the bubble, inflation continues, spawning more bubbles. If this is true, then our observable universe is just one bubble in an eternally inflating multiverse. There are infinitely many other bubbles, each potentially with different physical laws, if the laws of physics are set by symmetry-breaking phase transitions during inflation. This is deeply controversial. Some physicists embrace it as a natural consequence of the mathematics. Others reject it as untestable speculation, because if we can never observe other bubbles, how can we test the theory? Here's where we need to be careful. Science is based on testable predictions. If a theory makes no testable predictions, is it science? The multiverse idea does make some testable predictions. It predicts we should live in a typical bubble, not a special one. It predicts certain properties of our universe should be likely, given the range of possibilities. Physicists are working on ways to formalize these predictions. But it's fair to say this is the frontier of knowledge, where evidence is thin and theory is doing heavy lifting. Regardless of whether the multiverse idea is correct, the core of inflation, the idea that the early universe went through a period of exponential expansion, is on much firmer ground. The evidence from the CMB, from large-scale structure, from the flatness and uniformity of the universe, all point toward inflation or something very much like it. And the basic mechanism, a quantum field with vacuum energy driving expansion, is grounded in well-understood physics. So when we say the universe expanded faster than light, we're not speculating wildly. We're describing a phenomenon that fits a vast body of observational data and is predicted by theories that have been tested in multiple ways. Yes, there are still unknowns. Yes, there are speculative extensions of the theory. But the core idea is as well established as anything in cosmology. Now, let me hit you with something that might make you uncomfortable. If inflation is correct, and the universe is vastly larger than what we can observe, and if quantum fluctuations create structure randomly, then there are almost certainly other regions of the universe where the exact same arrangements of matter occurred as here. There are other planets like Earth, other people like you, living lives that are identical, down to the atomic level, up to some point, and then diverging due to quantum randomness. This isn't just a philosophical thought experiment. It's a consequence of combining a finite number of possible particle configurations, quantum mechanics, and infinite space, which inflation provides. If there are infinitely many regions the size of our observable universe, and only finitely many ways to arrange particles within each region, and by the pigeonhole principle, the same arrangements must repeat infinitely many times. Somewhere out there, there's another you, making the same choices, having the same thoughts, at least up until quantum randomness causes your paths to diverge. Does this bother you? It bothers some people. It makes them feel like they're not unique. But I'd argue it's actually empowering. It means that the specific configuration of matter that is you, your thoughts, your memories, your personality, is not just a random accident. It's something that the universe naturally produces, given enough space and time. You are a pattern that emerges from the laws of physics, and that pattern is stable and reproducible. That's remarkable. But let's get back to the central narrative. We've established that the universe expanded faster than light. We've explained how this happened without violating any physical laws, and we've surveyed the evidence that supports this picture. But there's a deeper question lurking underneath all of this. What does this mean for the nature of space and time themselves? Are they fundamental, or are they emergent from something deeper? This is where cutting-edge theoretical physics is heading, and it's going to blow your mind even more than what we've covered so far. We've talked a lot about space expanding, but we haven't really dug into what space is at the deepest level. In general relativity, space and time are merged into spacetime, a smooth, continuous four-dimensional fabric that can curve and stretch. But general relativity is a classical theory. It doesn't incorporate quantum mechanics, the physics of the very small. And when you try to combine general relativity with quantum mechanics, you run into problems. Deep, fundamental problems that suggest spacetime might not be as fundamental as we thought. Here's the issue. In quantum mechanics, everything is uncertain. Particles don't have definite positions or momenta until you measure them. They exist in superpositions, combinations of multiple possibilities. And this uncertainty extends to fields. The electromagnetic field fluctuates. Even in a vacuum with no particles present, the field jitters around due to quantum fluctuations. We've measured these fluctuations. They cause measurable effects like the Casimir effect and the Lamb shift. Quantum field theory, which describes particles as excitations in quantum fields, is the most successful theory in physics, predicting phenomena to extraordinary precision. But when you try to apply this quantum framework to spacetime itself, things break down. Spacetime in general relativity is smooth, but quantum mechanics suggests that at the smallest scales, spacetime should fluctuate wildly. At distances around the Planck length, about 10 to the negative 35 meters, the quantum fluctuations of spacetime should become so large that the very concept of distance or duration becomes meaningless. Space and time should foam and froth like boiling water, with tiny wormholes and black holes popping in and out of existence. This is called spacetime foam or quantum foam, and it's a real consequence of applying quantum mechanics to gravity. The problem is that general relativity assumes spacetime is smooth. When you try to calculate quantum corrections to general relativity, you get infinities, nonsensical answers that suggest the theory is incomplete. Physicists have been trying to solve this problem for decades, attempting to create a quantum theory of gravity, a theory that describes what happens to spacetime at the Planck scale. And the leading candidates for such a theory, string theory and loop quantum gravity, suggest that spacetime is not fundamental. It's emergent. String theory proposes that the fundamental entities are not particles, but tiny, vibrating strings. Different vibration modes of these strings correspond to different particles. Electrons, quarks, photons, even gravitons, the hypothetical particles of gravity, are all just strings vibrating in different ways. And in string theory, space and time emerge from the collective behavior of these strings. At large scales, the string's behavior averages out to create the smooth spacetime of general relativity. But at small scales, near the Planck length, the discrete, quantum nature of the strings becomes important, and spacetime dissolves into something more fundamental. Loop quantum gravity takes a different approach. It proposes that spacetime itself is quantized, made of discrete chunks. Just as matter is made of atoms, space is made of tiny loops of quantum geometry, connected in a network called a spin network. The smooth spacetime we experience is an approximation that emerges when you zoom out and average over many loops. But at the Planck scale, space is granular, like a fabric woven from threads. Both approaches suggest that the smooth, continuous spacetime of general relativity is an illusion, a useful approximation at scales we can currently probe, but not the ultimate reality. And if spacetime is emergent, then the expansion of space, the phenomenon we've been discussing this entire time, is also emergent. It's a large-scale consequence of deeper quantum processes happening at the Planck scale. Now you might be thinking, okay, but if we can't observe the Planck scale, if it's too small for any imaginable experiment to probe, how can we test these theories? And you're right to be skeptical. String theory and loop quantum gravity have been criticized for being untestable, but there are indirect ways to test them. If space-time is quantized, it might affect the propagation of light at very high energies. Photons of different energies might travel at slightly different speeds, an effect called quantum gravity dispersion. Observations of gamma-ray bursts, distant explosions that emit high-energy photons, can place limits on this effect. Additionally, quantum gravity theories make predictions about the very early universe. During inflation, the universe was so small and so energetic that quantum gravity effects might have been important. The imprint of these effects could be visible in the CMB. For instance, certain patterns in the CMB, polarization, or non-Gaussian features in the temperature fluctuations might signal quantum gravity. So far, we haven't seen such signals, but experiments are getting more sensitive. Even if we can't directly test quantum gravity, the mere fact that general relativity and quantum mechanics are incompatible tells us that our current understanding is incomplete. Something has to give. Either we find a way to quantize gravity, or we discover that quantum mechanics itself needs modification at large scales or high energies. Either way, there's deeper physics waiting to be uncovered. And this brings us back to inflation and the expansion of space. If space-time is emergent, then what does it mean for space to expand? Is expansion a real physical process, or is it just a convenient description of how the quantum substrate of reality behaves? These are open questions. Some physicists argue that the expansion of space is as real as anything else in physics. Space expands, galaxies get farther apart, light gets redshifted, and these are objective facts. Others argue that only relational properties are real, the distances between objects, the redshift of light, and that talking about space itself expanding is a choice of language, not a fundamental truth. This might seem like philosophical hair-splitting, but it has practical consequences. For instance, if you want to calculate the energy of the universe, you run into ambiguities. Energy is conserved locally, but in an expanding universe, global energy conservation becomes murky. The energy of matter and radiation dilutes as space expands. Dark energy increases as space expands. Does the total energy of the universe increase, decrease, or stay constant? The answer depends on how you define energy in general relativity, and different definitions give different answers. Some physicists, like Sean Carroll, argue that energy simply isn't conserved in an expanding universe, and that's fine. Conservation of energy is a consequence of time translation symmetry, the idea that the laws of physics don't change over time. In an expanding universe, time translation symmetry is broken because the universe looks different at different times. So energy conservation doesn't hold globally, and we shouldn't expect it to. Others, like Lawrence Krauss, argue that if you account for the gravitational energy of the universe, which is negative, the total energy is zero and conserved. The positive energy of matter and dark energy is exactly balanced by the negative gravitational energy. Both perspectives have merit, and the debate continues. What's clear is that our intuitions about space, time, and energy, shaped by everyday experience, break down when applied to the universe as a whole. The universe is not like objects within the universe. It doesn't sit in some external space or evolve in some external time. It is space and time. And trying to apply concepts like energy conservation, which make sense for systems within the universe, to the universe itself is tricky. But here's what's amazing. Despite these deep conceptual issues, the practical predictions of cosmology work. We can calculate what the CMB should look like, predict the abundance of elements, simulate the formation of galaxies, and our calculations match observations. The theories we use, general relativity and quantum field theory, incomplete as they may be at the deepest level, are fantastically successful at describing the universe we observe. This suggests that even if spacetime is emergent, even if there's deeper physics we don't yet understand, the emergent description we have is accurate for the scales we can currently probe. And this is a pattern in science. Newtonian mechanics is an approximation of relativity, valid at low speeds. Classical physics is an approximation of quantum mechanics, valid at large scales. General relativity is likely an approximation of some quantum theory of gravity, valid at scales larger than the Planck length. Each layer of theory is an effective description, accurate within its domain, but not the ultimate truth. And that's okay. Science doesn't claim to have final answers. It claims to have the best current answers, subject to revision as we learn more. So when we talk about the universe expanding faster than light during inflation, we're using the effective description provided by general relativity. At the scales inflation operated, well above the Planck scale, general relativity is an excellent approximation. The deeper quantum gravity effects, whatever they are, don't significantly change the picture. But at the very beginning, at the Planck time, about 10 to the negative 43 seconds after whatever initiated the Big Bang, quantum gravity effects would have been dominant, and our current theories break down. We can't reliably say what happened then. Maybe space-time itself didn't exist yet. Maybe it emerged from some pre-geometric quantum state. We don't know. This uncertainty at the very beginning is often misunderstood. Some people take it to mean that science can't explain the origin of the universe, leaving room for other explanations, philosophical or religious. But that's not quite right. Science is always a work in progress. The fact that we don't yet have a complete theory of quantum gravity doesn't mean we never will. And even without a complete theory, we have a remarkably detailed and successful description of the universe's history from a tiny fraction of a second after the Big Bang to the present day. That's an incredible achievement. Moreover, several approaches to quantum gravity and quantum cosmology offer speculative but intriguing ideas about the origin. Stephen Hawking and James Hartle proposed a model where the universe has no boundary in time, where the Big Bang is a smooth point in a quantum spacetime, not a singular beginning. Others, like Roger Penrose, propose cyclic models where the universe goes through infinite cycles of expansion and contraction. Still others suggest the universe emerged from a quantum fluctuation in a pre-existing vacuum state, a literal something from nothing if you interpret the quantum vacuum as nothing. These ideas are speculative, and we may never know which, if any, is correct. But they show that the question of origins is not off limits to science. It's just at the frontier, where evidence is scarce and theory does most of the work. And that's exciting. It means there's still so much to discover, so much we don't understand. The story of the universe is not finished. We're still writing it. Now, let's connect this back to you, the person watching this. You might be wondering, what does any of this have to do with me? Why should I care about the Planck scale, or quantum gravity, or the expansion of space billions of years ago? Here's why. Understanding where the universe came from and how it evolved gives us context for our own existence. We are made of atoms forged in stars, which themselves formed from gas clouds that condense due to gravity acting on density fluctuations seeded by inflation. The quantum jitter of the inflatoned field, stretched cosmic size, is the ultimate ancestor of every structure in the universe, including you. You are a product of the cosmos, shaped by its history. The laws of physics that governed inflation are the same laws that govern the chemistry in your body, the firing of neurons in your brain, the beating of your heart. You're not separate from the universe. You're a part of it, a way the universe has organized itself to become aware of itself. Carl Sagan said, "We are a way for the cosmos to know itself," and that's not poetic exaggeration. It's literal truth. The matter and energy in your body have been through stars, through interstellar space, through the Big Bang, through inflation, all the way back to the quantum fluctuations in the inflatoned field. And here's the kicker. If the universe is as vast as inflation suggests, if there are infinite regions beyond our observable horizon, then you're part of something incomprehensibly large. But you're also unique in your local region. The specific arrangement of atoms that makes you has never occurred before in the history of the observable universe, and will never occur again, unless you count those distant doppelgangers in far-off bubble universes. So you're simultaneously insignificant, a tiny part of a vast cosmos, and incredibly significant, a unique, unrepeatable pattern of matter and energy. This dual perspective, the cosmic and the personal, is one of the gifts of scientific understanding. It humbles us by showing how small we are, how brief our lives are compared to the age of the universe. But it also elevates us by showing that we're part of something grand, that our existence is connected to the deepest workings of reality. You're not just living on a planet. You're living in a universe that expanded from quantum fluctuations, that forged elements in stars, that organized matter into complexity, culminating in beings capable of understanding their own origins. That's extraordinary. Let's take a step back and talk about how we measure the universe's expansion. Because it's one thing to say space is expanding, and another to actually observe it and quantify it. The key tool astronomers use is redshift. When light travels through expanding space, its wavelength stretches. Light waves are like ripples on a pond, and if the pond itself is expanding, the ripples get longer, the distance between wave crests increases. For light, longer wavelength means redder color. Blue light shifts toward red light shifts toward infrared, and so on. This is cosmological redshift, and it's distinct from the Doppler shift you might have heard about. Doppler shift happens when a source of waves is moving through a medium. If a car drives toward you, honking its horn, the sound waves get compressed, and you hear a higher pitch. If it drives away, the waves get stretched, and you hear a lower pitch. Light does the same thing when an object moves toward or away from you through space. But cosmological redshift is different. It's not caused by galaxies moving through space. It's caused by space itself expanding, stretching the light waves as they travel. We can measure redshift by looking at the spectrum of light from distant galaxies. Atoms emit and absorb light at specific wavelengths, creating spectral lines. Hydrogen, for example, has a prominent line at 663 nanometers, a red wavelength. If we observe a distant galaxy and find this hydrogen line shifted to, say, 730 nanometers, that tells us the wavelength was stretched by about 10%. We quantify this with the redshift parameter, Z, defined as the fractional change in wavelength. In this example, Z would be about 0.1. The farther away a galaxy is, the more space there is between us and it, and the more that space has expanded while light was traveling, so the greater the redshift. Edwin Hubble discovered in the 1920s that there's a linear relationship between distance and redshift for nearby galaxies. The farther a galaxy, the faster it recedes. This relationship is called Hubble's law, and the proportionality constant is called the Hubble constant, usually denoted h0. But here's where things get subtle. The Hubble constant is not actually constant over time. It's the current expansion rate of the universe. In the past, when the universe was denser, gravity was stronger, and the expansion rate was different. As we look at galaxies farther away, we're looking back in time, seeing them as they were billions of years ago, when the expansion rate was different. So the relationship between distance and redshift is not perfectly linear for very distant galaxies. To accurately convert redshift to distance, we need to know the universe's entire expansion history, which depends on the mix of matter, radiation, and dark energy. Cosmologists have developed a framework for this, called the lambda-CDM model, where lambda represents dark energy and CDM stands for cold dark matter. This model describes how the universe expands over time, given the amounts of ordinary matter, dark energy, and radiation. When we plug in the values measured from the CMB and other observations, the model predicts how redshift relates to distance. And when we compare these predictions to observations of distant supernova, galaxies, and quasars, they match beautifully. But measuring distances in cosmology is notoriously tricky. For nearby objects, we can use parallax, the apparent shift in position as Earth orbits the Sun. For slightly farther objects, we use standard candles, objects with known luminosity. If you know how bright something truly is, and you measure how bright it appears, you can calculate its distance because brightness decreases with distance. Type Ia supernova are excellent standard candles. They're exploding white dwarf stars, and they always explode with roughly the same intrinsic brightness. By observing supernova in distant galaxies, astronomers can measure those galaxies' distances and compare them to redshifts. In 1998, two teams did exactly this and made a shocking discovery. They expected to find that the universe's expansion was slowing down due to gravity. Instead, they found it was speeding up. Distant supernovae were farther away than they should be if the expansion were decelerating, implying the expansion is accelerating. This discovery of cosmic acceleration implied the existence of dark energy, a mysterious form of energy with negative pressure that pushes space apart. Saul Perlmutter, Brian Schmidt, and Adam Rees led these teams and shared the 2011 Nobel Prize in Physics for this discovery. Dark energy makes up about 68% of the universe's total energy. Dark matter, which gravitates but doesn't emit light, makes up about 27%. Ordinary matter, the stuff of stars, planets, and us, is only about 5%. We live in a universe dominated by components we barely understand. Dark matter we've inferred from its gravitational effects on galaxies and galaxy clusters. It seems to be made of particles that don't interact with light, only with gravity. Several experiments are searching for dark matter particles, but so far, we haven't detected them directly. Dark energy is even more mysterious. We don't know what it is. The simplest explanation is that it's the cosmological constant, a constant energy density intrinsic to space itself, the same kind of vacuum energy that drove inflation, but much weaker. If the cosmological constant is the answer, then dark energy is truly a property of space, unchanging and eternal. But the value of the cosmological constant, implied by observations, is puzzlingly small. Naive calculations from quantum field theory predict a vacuum energy that's 10 to the 120 times larger than what we observe. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in physics. Some physicists think dark energy might not be constant. It might be a slowly evolving field, similar to the inflaton field, but with much lower energy. This is called quintessence. If dark energy is evolving, its effects on the universe's expansion would change over time, and we might be able to detect this by observing very distant supernova or by measuring the growth of cosmic structure. Future surveys will test these ideas. But let's get back to the expansion rate. There's currently a controversy in cosmology called the Hubble tension. When we measure the Hubble constant by observing nearby supernova and using other local distance indicators, we get a value around 73 kilometers per second per megaparsec. But when we infer the Hubble constant from the CMB using the lambda CDM model, we get about 67. These values don't agree within measurement uncertainties. Either one of the measurements is wrong, or the lambda CDM model is incomplete, missing some new physics. This tension is exciting because it might be pointing us toward new discoveries. Maybe dark energy is more complicated than a cosmological constant. Maybe there's an extra component of energy or matter we haven't accounted for. Maybe general relativity needs modification. Or maybe one of the measurement methods has a subtle systematic error. Astronomers and cosmologists are working hard to resolve this, and the answer, whatever it is, will teach us something new about the universe. Now, let's talk about the future of the universe's expansion. Right now, the universe is expanding and accelerating. If dark energy remains constant, as current observations suggest, then the universe will continue to accelerate forever. Distant galaxies will recede faster and faster, eventually crossing our event horizon and disappearing from view. In the far future, trillions of years from now, Only our local group of galaxies, held together by gravity, will remain visible. The rest of the universe will have receded beyond our observable horizon. Eventually, stars will burn out. The universe will fill with black holes and cold, dead remnants. The black holes will slowly evaporate due to Hawking radiation, a quantum process where black holes emit particles and lose mass over unimaginably long timescales. After 10 to the 100 years, even the largest black holes will have evaporated. What's left will be a cold, dark, empty universe with nothing but scattered photons and particles, diluted to almost nothing by the relentless expansion of space. This is called the heat death or big freeze, and it's the likely fate of the universe if current trends continue. But there's a caveat. Our understanding of dark energy is limited. If dark energy is not constant, if it's evolving, then the future could be different. Some models predict dark energy could strengthen, eventually becoming so powerful it tears apart galaxies, stars, planets, even atoms in an event called the Big Rip. Other models predict dark energy could weaken or even reverse, causing the universe to stop expanding and start contracting, leading to a big crunch. We don't know which, if any, of these scenarios will happen. Our observations only constrain the present and recent past. Predicting the distant future requires extrapolating beyond what we can currently measure. But here's the important point. The expansion of the universe is not just a feature of the early universe. It's ongoing. Every second, space is expanding, carrying galaxies apart. The universe you live in today is larger than it was yesterday and smaller than it will be tomorrow. This is happening continuously, driven by the strange properties of dark energy that we're only beginning to understand. And this connects back to inflation, because inflation and the current acceleration due to dark energy are conceptually similar. Both involve vacuum energy with negative pressure, causing space to expand rapidly. The difference is in the magnitude. Inflation was vastly more powerful, driving exponential expansion in a tiny fraction of a second. The current acceleration is gentle, barely noticeable over human timescales. But both are manifestations of the same basic physics: vacuum energy affecting the expansion of space. This raises a tantalizing question. Could inflation happen again? Could some quantum fluctuation trigger a new phase of inflation in some region of space, creating a new inflating bubble within our universe? This is called vacuum decay, and it's a theoretical possibility. If the vacuum state of our universe is not the absolute lowest energy state, if there's a deeper, more stable vacuum, then a quantum fluctuation could trigger a transition. A bubble of the new vacuum would form and expand at the speed of light, obliterating everything in its path, rewriting the laws of physics inside the bubble. This sounds terrifying, but the timescales are so long and the probabilities so low that it's not a practical concern. The universe would likely end in heat death long before vacuum decay became an issue. But it's a reminder that the universe is a dynamic, evolving entity. Space is not a static stage. It's an active participant in cosmic history, expanding, stretching, potentially transitioning to new states. And understanding this requires bringing together general relativity, quantum mechanics, thermodynamics, and observational astronomy. It's a multidisciplinary effort, combining theoretical insights with empirical data, and it's one of the most exciting frontiers of human knowledge. So when you look up at the night sky, remember, the light from those stars and galaxies traveled through expanding space to reach you. The photons were stretched, redshifted by the expansion. The galaxies themselves are farther away now than they were when the light left them. You're looking at a universe in motion, a universe growing, evolving, heading toward an uncertain future. And you're part of that story, a brief but bright flicker of complexity in an expanding cosmos. Let's dive into one of the most philosophically provocative implications of inflation, the idea that the universe might be eternal into the past and into the future, not in the sense of being static, but in the sense of continuously inflating in some regions. This is called eternal inflation, and it's a mind-bending concept that challenges our intuitions about beginnings and endings. The basic idea is this: inflation doesn't necessarily end everywhere at once. In some regions, quantum fluctuations can cause the inflattened field to jump back up to a higher energy state where inflation resumes. This creates a patchwork of inflating and non-inflating regions. In the non-inflating regions, like our observable universe, inflation has ended and a hot Big Bang phase begins. But in the still inflating regions, space continues to expand exponentially, and new non-inflating bubbles can form within them. Because space is expanding exponentially in the inflating regions, the volume of inflating space increases faster than it gets converted to non-inflating space. Even though new bubble universes are constantly forming, the total volume of inflating space grows without bound. Inflation never stops in totality. It's eternal to the future. And some versions of the theory suggest it might be eternal to the past as well, with no absolute beginning, just an eternally inflating multiverse where Big Bangs are continuously happening in localized bubbles. This picture has profound implications. If inflation is eternal, then the observable universe is not the universe. It's one bubble among countless others, each with its own Big Bang, its own history, possibly its own physical constants and laws of physics, if those are set by random symmetry breaking during a phase transition that ends inflation. We would live in a multiverse, a vast ensemble of bubble universes, most of which are forever beyond our reach. Now, this is speculative. Eternal inflation is a prediction of some inflationary models, but it's not confirmed observationally. And there are significant challenges to the idea. For one, if inflation is eternal to the past, does that avoid the need for an absolute beginning? Not necessarily. Arvind Borde, Alan Guth, and Alexander Valenkin proved a theorem called the BGV theorem, showing that any universe that is, on average, expanding cannot be eternal to the past. It must have a boundary, a point before which it didn't exist, at least not in a classical sense. This suggests that even eternal inflation must have had a beginning, though what that beginning was, and whether it even makes sense to talk about time before it, is unclear. Some cosmologists propose that the beginning was a quantum event, a fluctuation from nothing, or from some pre-existing quantum state that initiated inflation. Others suggest the beginning was a singularity, like the Big Bang singularity, but in a more fundamental theory of quantum gravity. Still others argue that time itself is emergent, and asking what happened before the beginning is like asking what's north of the North Pole. The question doesn't make sense, because there's no before. These are deep, perhaps unanswerable questions, but they illustrate how far we've come in our understanding and how much further we have to go. We've gone from not knowing the universe was expanding less than 100 years ago to contemplating the nature of time, the existence of multiverses, and the quantum origins of everything. That's remarkable progress. Let's talk about another implication of inflation that's closer to testable science: the possibility of observing gravitational waves from inflation. During inflation, quantum fluctuations don't just create density fluctuations. They also create gravitational waves, ripples in the fabric of spacetime itself. These primordial gravitational waves would have specific properties, a nearly scale-invariant spectrum, and they would leave an imprint on the CMB in the form of B-mode polarization, a particular pattern in how the CMB light is polarized. Detecting this signal would be a smoking gun for inflation. It would confirm that inflation happened and give us information about the energy scale of inflation, how violent and energetic the process was. Several experiments are currently searching for this signal. The BICEP and Keck array experiments, located at the South Pole, are scanning the sky for B-modes. So far, they found hints of a signal, but it's contaminated by foreground emission from dust in our galaxy, making it hard to confirm. Future satellites, like LIGHT-BRD and CMBS-4, will have better sensitivity and might detect primordial B modes if they're strong enough. If we detect them, it will be a triumph for theoretical physics. Inflation, proposed in the 1980s based on theoretical considerations and refined over decades, will have been confirmed by direct observational evidence. And the properties of the gravitational wave signal will tell us about the inflaton field, its potential energy curve, and the dynamics of inflation. It would be like having a direct window into the first fraction of a second of cosmic history. But even if we don't detect primordial gravitational waves, that tells us something. It would mean inflation happened at a lower energy scale than some models predict, ruling out certain versions of the theory and guiding us toward others. Science progresses both by confirming predictions and by ruling out possibilities. Either outcome advances our understanding. Now, let's connect this to you again. Why should you care about primordial gravitational waves or eternal inflation? Because these ideas are pushing the boundaries of what we can know about reality. They're forcing us to confront questions about the nature of existence, the origins of the universe, and our place within it. These aren't just academic puzzles. They're part of the human quest to understand where we came from and why the universe is the way it is. And here's something beautiful. You don't need a PhD in physics to appreciate these ideas. You just need curiosity and a willingness to grapple with concepts that challenge your intuitions. The universe is stranger and more wonderful than everyday experience suggests, and science is the tool we've developed to explore that strangeness. By engaging with these ideas, even at a conceptual level, you're participating in one of humanity's greatest intellectual adventures. Think about it. 100 years ago, we didn't know galaxies existed. We thought the Milky Way was the entire universe. Now we know there are trillions of galaxies spread across an expanding universe that might be part of an infinite multiverse. That's an incredible expansion of our cosmic horizon, and it happened because people were curious, asked questions, built instruments, and followed the evidence wherever it led. You're living at a remarkable time in human history. We have tools to observe the universe with unprecedented clarity. We have theories that connect the quantum world to the cosmos. We're on the verge of answering some of the deepest questions ever asked, and you get to witness this. You get to know what previous generations could only wonder about. That's a privilege. Let's talk about one of the most counterintuitive aspects of the expanding universe, the idea that there's no center to the expansion. People often imagine the Big Bang as an explosion in space, with galaxies flying outward from some central point. But that's not right. The Big Bang happened everywhere at once. Space itself expanded, and it expanded uniformly in all directions. Every point in space can claim to be the center, or equivalently, there's no center at all. Think of it like this. Imagine the surface of a balloon. Draw dots on the balloon to represent galaxies. Now inflate the balloon. Every dot moves away from every other dot. If you stand on any one dot and look around, you see all the other dots receding from you. You might think you're at the center, but if you jump to any other dot, you see the same thing. All dots are equivalent. There's no special central dot. The surface of the balloon is expanding, and the dots are just going along for the ride. Now, the balloon analogy has limitations. The surface of a balloon is two-dimensional, curved into a three-dimensional space. The universe is three-dimensional, possibly curved into a higher dimensional space, though we don't experience that higher dimension. But the key point holds. The universe expands uniformly, and every location sees the same expansion. This is called the cosmological principle, the idea that the universe is homogeneous and isotropic, the same everywhere and in all directions, at least on large scales. Observations support this. A CMB looks almost identical in all directions, with temperature variations of only 1 part in 100,000. The distribution of galaxies, when averaged over large volumes, is roughly uniform. There's no evidence for a center or an edge to the universe. As far as we can tell, The universe extends indefinitely in all directions, possibly infinitely. But there's a subtlety. Even though there's no center in space, there is a sense in which every observer has their own cosmic horizon. The observable universe is the region of space from which light has had time to reach us since the Big Bang. For us, that's a sphere centered on us, about 93 billion light-years in radius. But an observer in a distant galaxy would have their own observable universe, a sphere centered on them. These spheres overlap, but are not identical. And because the universe is expanding, and distant regions are receding faster than light due to the expansion of space, there are galaxies that we can see now, but whose light will never reach us again in the future. Their future light is being emitted into a space that's expanding away from us, faster than light can catch up. We are surrounded by an event horizon, and as dark energy drives accelerated expansion, this horizon shrinks. Galaxies cross it and disappear from view, not because they're destroyed, but because we lose causal contact with them. This means the observable universe is not fixed. It evolves. Early in the universe's history, when everything was closer together, the observable universe was smaller. In the future, as distant galaxies cross the event horizon, the observable universe will shrink in terms of the number of galaxies we can see, even as the physical size of our observable region continues to expand. This is a strange and somewhat melancholy thought. We're living in a brief epoch, cosmologically speaking, where the universe is observable. In the far future, civilizations, if any exist, will look out and see only a handful of nearby galaxies, held together by gravity, surrounded by darkness. They might not even realize the universe is expanding because all the distant galaxies, the ones we see today and used to measure the expansion, will have crossed the event horizon. They'll have no evidence for the Big Bang, no CMB, no distant supernova. Their cosmology will be impoverished compared to ours. This makes our time special. We're living when the universe is observable, when we can see its history written in the light from distant galaxies and the afterglow of the Big Bang. We're living when the evidence for the universe's grand story is accessible. And we're the first generation in human history to have the tools and knowledge to read that story. That's extraordinary. But let's not get too anthropocentric. The universe doesn't care about us. It's not expanding for our benefit. The fact that we happen to exist at a time when the universe is observable is partly selection bias. If the universe weren't observable, we might not be here to wonder about it. Complex structures like galaxies, stars, and planets formed during a particular era of the universe's history, after it cooled enough for matter to clump, but before acceleration drove everything too far apart. We necessarily live during that era because that's when life-friendly conditions exist. This is an application of the anthropic principle, the idea that observations of the universe are constrained by the requirement that observers exist. It's a controversial principle. Some physicists embrace it as a useful tool for understanding why the universe has the properties it does. Others reject it as unscientific, a way of avoiding deeper explanations. The debate continues. But regardless of how you feel about the anthropic principle, the fact remains. We're here, we're observing, and what we're observing is a universe that expanded from a hot, dense state, went through a period of exponential inflation, cooled and formed structure, and is now accelerating toward a cold, empty future. That's the story the evidence tells, and it's a story that's both humbling and awe-inspiring. Now, let's talk about what it means for space to be infinite. If the universe is spatially flat, as observations suggest, and if it extends indefinitely, then it's infinite. Infinite space means infinite matter, infinite galaxies, infinite stars. It means that somewhere out there, every possible arrangement of matter that can occur, given the laws of physics, does occur infinitely many times. There are regions identical to our solar system, regions where there's another Earth with another you, living a life identical to yours up to some point, and then diverging due to quantum randomness. This is deeply weird. It means you're not unique, not in the cosmic sense. There are copies of you, exact duplicates down to the atomic level, scattered throughout the infinite expanse of space. These duplicates are so far away that you'll never meet them, never interact with them, never even see the light from their region of space, because they're beyond your cosmic horizon. But they exist if the universe is truly infinite. Some people find this disturbing. It challenges the sense of individuality, the feeling that you're a singular, unique being. But I'd argue it's actually comforting. It means that the pattern that is you is robust, reproducible, a natural consequence of the laws of physics. You're not a fluke. You're something the universe creates, given enough space and time. And even if there are infinite copies of you, the subjective experience of being you, your qualia, your consciousness, is yours and yours alone. The copies might be physically identical, but they're not you. They're separate streams of consciousness, living separate lives. This gets into philosophy of mind and personal identity, topics beyond the scope of this script. But the point is that infinity, whether it's an infinite universe or an infinite multiverse, raises profound questions about identity, existence, and meaning. And these questions are not just abstract. They're deeply personal. They affect how you see yourself and your place in the cosmos. So when you think about the universe expanding faster than light during inflation, remember that this expansion didn't just make the universe big. It made it unimaginably big, possibly infinite, and it seeded the structure that led to galaxies, stars, planets, and you. The fast expansion of the early universe is not a distant, irrelevant fact. It's the foundation of everything you see and are. We're nearing the end of our journey, but there's one more layer to peel back: the relationship between the expansion of space and the flow of time. In general relativity, space and time are not separate. They're interwoven into spacetime, a single four-dimensional entity. When space expands, it affects time and vice versa. This leads to some truly mind-bending consequences. One is time dilation due to the expansion of the universe. When we observe a distant galaxy, we're seeing it as it was billions of years ago, because light takes time to travel. But we're also seeing it in a time-dilated state. Events in that galaxy appear to happen more slowly than they would locally because of the expansion of space. Supernova in distant galaxies, for example, appear to fade more slowly than nearby supernova, not because they're intrinsically different, but because the light from later stages of the explosion is stretched by the expansion of space, effectively slowing down the observed evolution. This time dilation is a real effect, confirmed by observations. It's another piece of evidence that space is expanding. If galaxies were just moving through a static space, we wouldn't see this time dilation. The fact that we do tells us that the expansion of space affects the passage of time for distant objects as we observe them. Another consequence is the relativity of simultaneity in an expanding universe. In special relativity, simultaneity is relative. Events that are simultaneous for one observer are not simultaneous for another observer moving at a different velocity. In an expanding universe, this becomes even more complex. Because space is expanding, distant galaxies are receding from us, and the concept of now for a distant galaxy is ambiguous. There's no universal clock ticking away the same time for the entire universe. We can define a cosmic time, a time coordinate that corresponds to the time measured by observers at rest with respect to the cosmic expansion. Essentially, observers who see the CMB as isotropic. This cosmic time is useful for cosmology because it gives a consistent way to talk about the age and evolution of the universe. But it's a choice of coordinates, not a fundamental aspect of reality. Different observers could choose different time coordinates, and all would be equally valid. This relativity of time is one of the hardest concepts in relativity to grasp. We intuitively think of time as absolute, flowing the same for everyone. But relativity tells us that's not true. Time is relative, intertwined with space, and affected by motion and gravity. In an expanding universe, time is also affected by the expansion itself. Now, here's a question that often comes up. If space is expanding, does that mean the atoms in our bodies are expanding? Are we getting bigger? The answer is no, and understanding why is important. The expansion of space only affects objects that are not bound together by forces stronger than the expansion. Galaxies and galaxy clusters are gravitationally bound, so they don't expand. The Milky Way and Andromeda are part of the local group, which is gravitationally bound, so the expansion of space doesn't push them apart. In fact, the Milky Way and Andromeda are on a collision course due to their mutual gravitational attraction overcoming the local expansion of space. On smaller scales, forces are even stronger. Atoms are held together by electromagnetic forces, which are vastly stronger than the expansion of space at those scales. Molecules, cells, planets, stars, all are bound by forces that completely dominate over the expansion. The expansion of space only matters on scales where objects are not gravitationally or otherwise bound, roughly on scales larger than galaxy clusters. So no, you're not expanding. Your atoms are not expanding. The Earth is not expanding. The expansion of space is a large-scale phenomenon, relevant for understanding the universe as a whole, but not for everyday objects. This is a relief, because if we were expanding along with space, we'd never notice the expansion. It's only because we're not expanding that we can observe distant galaxies receding. Let's talk about one final, profound implication of the expanding universe: the ultimate fate of information. In physics, information is a technical concept related to the state of a system. If you know the exact state of a system at one time, and you know the laws of physics, you can predict its state at any future time and retrodict its state at any past time. This is called determinism, and it's a feature of classical physics and, in a more subtle way, of quantum mechanics. But in an expanding universe, especially one with an event horizon due to accelerated expansion, information can be lost. If a galaxy crosses our event horizon, we lose the ability to receive information from it. Any signal it sends will never reach us. In that sense, information from that galaxy is lost to us, not destroyed, but inaccessible. And if the universe continues to expand and accelerate forever, more and more information will become inaccessible until we're left in a local bubble, isolated from the rest of the cosmos. This raises questions about the ultimate fate of consciousness, complexity, and life. Can civilization survive in a universe that's becoming increasingly isolated and depleted? Some physicists, like Freeman Dyson, have speculated about strategies for survival, spreading out to avoid heat death, extracting energy from the quantum vacuum, or exploiting obscure thermodynamic loopholes. Others, like Frank Tipler, have proposed that advanced civilizations might manipulate spacetime itself, creating closed time-like curves or affecting the universe's global structure. These ideas are highly speculative, bordering on science fiction, but they're grounded in real physics, pushing the boundaries of what's possible within the laws of nature. And they remind us that the universe's fate is not just an abstract concern. If life and consciousness are to persist, they must contend with the realities of cosmology. The expansion of space, driven by dark energy, is one of those realities. But here's an optimistic thought. We don't know what dark energy is. We don't know if it will remain constant. A universe might surprise us. The far future might be very different from our current projections. Betting against the creativity and adaptability of life, and by extension, intelligence, seems unwise. We've survived and thrived in a dynamic, changing universe so far. Who's to say we, or our descendants, won't find ways to continue doing so, no matter what the cosmos throws at us? And even if the universe ends in heat death, or a big rip, or some other cosmic catastrophe, the fact remains that for a brief, shining moment, the universe organized itself into structures complex enough to contemplate their own origins and fate. Stars formed, planets coalesced, life emerged, intelligence evolved. we exist. We think. We wonder. That's extraordinary, regardless of how long it lasts. Carl Sagan said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." That's as true today as when he said it. You are a collection of atoms forged in the nuclear furnaces of stars, blown into space by supernova, gathered into a planet by gravity, organized by evolution into a thinking, feeling being. You're a part of the universe that can reflect on the universe. That's a privilege and a responsibility. The universe doesn't care what you think or do. It's indifferent, but you care. And that makes all the difference. You give meaning to your existence through your actions, your relationships, your curiosity, your creativity. The universe provides the stage and the materials. You write the play. So let's bring this all together. We started with a puzzle. If nothing can go faster than light, how did the universe expand so fast during inflation? The answer, as we've explored in depth, is that the speed limit applies to motion through space, not to the expansion of space itself. Space can expand as fast as it wants, and during inflation, it expanded exponentially fast, doubling in size every unimaginably short interval, driven by the energy of a quantum field called the inflaton. This exponential expansion solved major cosmological problems, explaining why the universe is so flat, so uniform, and why it has the structure we observe. It's supported by multiple lines of evidence, from the CMB to the distribution of galaxies to the abundance of light elements. And it's a natural prediction of combining general relativity with quantum field theory, two of the most successful theories in all of physics. But inflation also raises profound questions. What is the inflaton field? What caused inflation to start? Did it have a beginning? Is our universe part of an eternally inflating multiverse? These questions push us to the edge of current knowledge, into territory where observation is scarce and theory speculates. And that's okay. Science is always a work in progress. The fact that we don't have all the answers doesn't diminish what we've achieved. It motivates us to keep searching. And the search continues. New experiments are being built to observe the CMB in greater detail, to search for primordial gravitational waves, to map the distribution of galaxies and dark matter. New telescopes, like the James Webb Space Telescope, are peering back to the earliest galaxies, seeing the universe as it was just a few 100 million years after the Big Bang. Particle accelerators are probing higher energies, searching for new particles and forces that might be connected to cosmology. We're living in a golden age of cosmology. The universe is revealing its secrets, and we're here to witness it. The story of how the universe expanded faster than light is just one chapter in a much larger story. The story of the cosmos, from its quantum origins to its ultimate fate and our place within it. And here's the final, most important point. You're part of this story, not as a passive observer, but as an active participant. Your existence is made possible by the expansion of the universe, by the formation of structure, by the nuclear reactions in stars. And your curiosity, your desire to understand, is a testament to the power of intelligence to make sense of complexity. You're a way for the universe to understand itself, and that's beautiful. So the next time you look up at the night sky, remember what you're seeing. You're seeing light that's traveled for billions of years, stretched by the expansion of space, coming from galaxies that are now far beyond our reach. You're seeing the universe as it was, not as it is. And you're seeing the consequences of events that happened in the first fraction of a second after the Big Bang, when space expanded faster than light, setting the stage for everything that followed. The universe is vast, ancient, and strange, but it's also knowable. Through science, through observation, through the power of mathematics and reason, we can understand it. We can trace the history of the cosmos, from the quantum fluctuations of inflation to the formation of galaxies to the emergence of life. We can ask the deepest questions and find answers grounded in evidence and logic. And that's the gift of science. It's not just a body of knowledge. It's a way of thinking, a method for uncovering truth, a tool for satisfying curiosity. It's humanity's greatest invention, and it's available to anyone willing to engage with it. So stay curious. Keep asking questions. Never stop wondering. The universe has so much more to teach us, and the journey of discovery is far from over. Whether it's understanding the nature of dark energy, detecting gravitational waves from inflation, finding evidence for the multiverse, or discovering how life and intelligence can persist in an expanding cosmos, there's always more to learn. You've made it through this epic journey, nearly 4 hours of diving deep into one of the most profound questions in all of cosmology. If you've stayed with me this far, thank you. You're the kind of person who doesn't settle for easy answers, who's willing to grapple with complexity, who finds joy in understanding. And that's what it takes to appreciate the universe in all its grandeur. Before we wrap up, I want to leave you with this thought. The fact that nothing can beat light, yet the universe expanded faster than light, is not a contradiction. It's a revelation. It tells us that reality is more nuanced, more layered than simple rules suggest. The universe found a loophole, not by breaking the laws, but by operating in a domain where those laws don't apply. And that loophole, the expansion of space itself, is responsible for the entire observable cosmos. You live in a universe that's larger, older, and stranger than you ever imagined. A universe that began from quantum fluctuations smaller than an atom and grew to cosmic scales in less than the blink of an eye. A universe where space itself is dynamic, where time is relative, where the very fabric of reality can stretch, bend, and expand. And you're a part of that universe, a thinking, feeling, curious part, trying to make sense of it all. That's incredible. Never forget that. You're not just living in the universe. You're a way for the universe to experience itself, to understand itself, to marvel at itself. And in doing so, you're participating in something cosmic, something timeless, something beautiful. Thank you for joining me on this journey. Keep looking up, keep wondering, keep learning. The universe is waiting to share more of its secrets with you. And who knows, maybe someday you'll be the one making the next great discovery, answering the next big question, pushing the boundaries of what we know even further. Until then, stay curious, stay skeptical, and stay amazed. The cosmos is yours to explore. Make the most of it.